Hello, Internet. We are live.
Hey everyone, welcome to episode 49 of the Stanford MLSys seminar series, coming back after a pretty long winter break. Also, this is episode 49, which means it's actually 50 because we start with zero. So really glad to be back. And we're also back with the Stanford class for the new quarter. So welcome to them as well. I'm Karan. We have with us as always, Dan.
Hey.
Hi, Dan. Fyodor.
Good to be back.
And our guest today, Beidi Chen, who
Hi.
is a postdoc in the computer science department at Stanford, working with Chris Ray. Her research focuses on large-scale machine learning and deep learning, especially looking at designing algorithms to accelerate machine learning workloads using things like sparsity. I believe that today she's going to talk to us about Pixelated Butterfly, so simple and efficient sparse training for neural nets. And before we take it away, I just want to remind the audience that this is a 30-minute podcast followed by a 30-minute talk followed by a 30-minute podcast style discussion where you and the live audience can ask questions. And if you're on YouTube, you can ask questions during the talk as well, and we will keep track of them and get them across to Beidi. So Beidi, take it away.
Sure. Can everybody see my slides? Cool. Hi, I'm Beidi. I'll present our recent work, Pixelated Butterfly, simple and efficient sparse training for neural network models. This is a joint work with my wonderful collaborators, Tree, Kai Zhao, Jiaming, Zhao, Atri, and Chris. In recent years, we've seen successful applications of machine learning models in scientific discovery, education, and user recommendation, especially with the rise of large models, AlphaFold, GPT-3, DALL-E, DRM. But large models trained on complex and rapidly growing data consume a lot of computational resources. For example, a single training run of GPT-3 takes a month on 1,100 GPUs and costs over 10 million. If you take a look at the size of the models and data, it's just exploding these days. With limited resources in practice, we need to overcome the bottlenecks and find more efficient ways to do this large-scale training. Otherwise, it's hard for example, academia friends to conduct related research. And for industry friends who might have access to more resources, the latency is still a concern, especially for some online services or frequent retraining. Imagine an ideal model. You should use less compute and memory while can still retain the generalization benefit of large ones. So the simplest and most popular direction is to sparsify these models. The idea of sparsity has a long history in machine learning and has driven fundamental progress in other fields like stats, neuroscience, and signal processing. Sparse training is an active research topic, and there's great work on the model compression side like pruning or lottery tickets. And there are excellent works on matrix approximation, side like all variants of efficient transformers, since reformer and Colossal from our Colossal tree. I've been working on this problem and has a series of work over the past few years as well. Besides the techniques, I like all the names: slide, mongoose, scatterbrain. So despite the significant efforts, speeding up sparse training on current deep learning hardware like GPUs without degrading accuracy still remains an unsolved problem. And in this talk, we'll show you how you can use simple static sparsity and train GPT-2, VIT, and MLP-Mixer up to 2.5 times faster while maintaining the same accuracy. Why is it so challenging to speed up training? How can we widen the adoption of sparse models? First, it's very difficult and expensive to search and find the sparsity pattern that could maintain the same level of accuracy of dense models. is a combinatorial problem. Many methods like pruning, logarithmic hashing needs to maintain dynamic sparsity mask, but the large overhead of evolving the sparsity mask can significantly slow down training instead of speeding it up and complicate the implementation. Second, most existing methods adopt unstructured sparsity, which may be efficient in theory, but do not take into account the efficiency of training hardware such as GPUs, which are pretty optimized for dense computation. Finally, most methods target on a single type of operation, for example, attention. But neural network models often compose different modules, like attention, MLP, and in many applications, MLP layers are actually the main training bottleneck. So ideal sparsity pattern would be static, structured, aligned with current hardware, and have wide coverage of operators that can apply to most of the neural network layers. And in this talk, I will show such sparsity pattern do exist. This is a sneak peek of our finding in our early exploration. We observed that one sparsity pattern, butterfly plus low rank, consistently outperformed the others. And this sparsity pattern closely connects to two lines of work in matrix structures. But before going to the details, I need to take a detour to briefly introduce several concepts and their applications for better understanding. One is the sparse plus low rank matrices, and the other one is called butterfly matrices. Then I will show Pixelated Butterfly, which draws inspiration from those matrices and their theoretical properties. And last, I will show the exciting experiment results, evaluating our sparse model in end-to-end training on vision and language tasks, downstream evaluation, and how close its empirical neural tangent kernel is to the dense models. Sparse, low rank approximation has been leveraged to approximate attention matrix, trading accuracy for efficiency. And we can basically characterize them into two major groups, exploiting either the sparsity like sparse transformer, reformer, routing transformer, or low rank property of the attention matrix like linformer, linear transformer, poleformer, and more. However, they're not that widely used because of the problem of their accuracy efficiency trade-off on different tasks. So can we combine the benefits of sparse and low rank? It turns out the sparse plus low rank matrix structure has been well studied in statistics and signal processing since the late 2000s. This structure naturally generalizes low rank and sparse matrices, and it has been rediscovered in efficient transformer context and optimal transport setting. Here's an example in our scatterbrain paper that if you combine reformer as the sparse component and performer as the low rank component in a simple way, you will get probably better approximation. The key message here is sparse plus low rank can do better approximation than sparse or low rank alone. The next concept is one class of matrix that is the central of our method called butterfly, which encodes the divide and conquer structure of fast transform algorithms such as FFT. Divide and conquer means if you perform a transform of size n, say the discrete Fourier transform, you can break that down into two transform of size n divided by 2 and so on. And how does this translate to the language of sparse factorization? So there's a class of fast linear maps that encodes this schema called butterfly. Each butterfly matrix is a product of log n sparse factors, and each having 2n non-zeros. And you can see it in the diagram. The red dots indicates the locations of non-zeros. the sparsity pattern is fixed and represents the recursion tree you bottom up. And those are trainable with gradient descent on just the non-zero entries of the butterfly matrix, which is a nice, smooth optimization problem. So the butterfly matrix is learnable and can capture the recursive divide-and-conquer structure. We can compose several butterfly matrices together to increase expressiveness. What's really nice about the products that they can represent any sparse matrix with near optimal space and time complexity, even with a fixed sparsity pattern. So back to our topic, we're sidestepping the combinatorial problem of searching over all the possible sparsity pattern at a minor cost and extra log factor in a number of parameters. So we'll come back to our key observation that butterfly plus low rank consistently outperform the others. This sparsity pattern enjoy the property of both sparse plus low rank matrix, which can capture the global and local information, and a butterfly matrix whose product can tightly represent any sparse matrix. Using the static sparsity pattern from butterfly, with the addition of a low rank term, would address 2 of 3 our challenges or concerns earlier. Its fixed pattern avoids the overhead of dynamic sparsity and yields a simple way to sparsify most neural network layers that are based on matrix multiplication. But butterfly matrices are inefficient on modern hardware. So next, we're getting into the design details of Pixelated Butterfly. I listed 3 challenges of butterfly matrix on modern hardware like GPUs on the left, and 3 simple changes on the right, which makes butterfly efficient while retaining their favorable properties. And I will go through them one by one. First, they're not hardware friendly because the sparsity pattern are not block aligned, while hardware like GPU, TPU are a block device. So we propose block butterfly matrices which operate on the block level, yielding a block aligned sparsity pattern. And the second one is, even they're block aligned, they're difficult to parallelize. They contain a sequential products of many factors. So we introduce flat butterfly, a first order approximation of butterfly matrices with residual connection that turns the original product of vectors into a sum. So basically their matrix implications are easy to parallelize. So now we have flat block butterfly, which is very efficient. But the third problem is they necessarily are high rank and cannot represent low rank matrices. If you notice the pattern we just saw, they're all diagonal stripes. But fortunately, we have a low rank term, which is efficient to compute and also increase the expressiveness. So putting everything together, our proposal combines flat block butterfly and low rank matrices to yield a simple and efficient sparse training method. It applies to most major bottlenecks of the neural network that rely on the matrix multiplication. Here's the workflow. Given the model schema and compute budget, we can pick a simple sparsity pattern based on flat block butterfly and use that to produce sparse mask for attention and also MLP layers. We also show it enjoys several nice theoretical properties inherited from our previous work, kaleidoscope and scatterbrain, which is butterfly and the sparse plus low rank structure. We proved that block butterfly retains the expressiveness of butterfly, and the flat butterfly can accurately approximate the residual form. Also, flat block butterfly plus low rank, which is naturally an instance of sparse plus low rank structure, is more expressive than sparse or low rank matrices alone. And last, we also analyze the training convergence and generalization of networks with sparse weights and show that training wide and sparse network with gradient descent converge globally, which is a direct extension from the result for wide dense layers. Okay, here comes the most exciting part, probably everybody's waiting for, the experiments. The first evaluation is on the standard image classification task, including CFAR and ImageNet. We conduct experiments on emerging MLP-Mixer and vision transformer models. We show that even with a very simple fixed sparsity, we managed to train models up to 2.3 times faster than the dense model without hurting model accuracy. And there are more details about the results and other sparse baselines in our paper. Check it out. And the second evaluation is on language modeling and classification task. The table on the left shows the result compared to the GPT-2 small and medium on Wikitext 103. Again, we show that we can train model up to 2.5 times faster than dense model without accuracy loss. Here we can also say a bit about the scaling law of the pixelated butterfly. So there's basically more savings with larger models. If you run actual GPT-2 1.5 billion model, or even to the scale of GPT-3, we anticipate the sparse model will have more benefits. And the table on the right shows the results compared to vanilla transformer on the long-range arena task, where the attention is the bottleneck. And pixelated butterfly is also able to maintain the accuracy. It's 5 times speed up. Besides the above results that was in the paper, to further understand our sparse model and evaluate the quality more thoroughly, over the break, we perform additional experiments, training open web text and open source version of what GPT-2 was trained on from scratch and evaluate on some downstream tasks in zero-shot fashion. So the results suggest that we can have large, sparse pre-trained language model that works as well on downstream. In addition, theory suggests that the neural tangent kernel dictates the generalization properties of overparameterized models. And close NTK distance suggests that our sparse model generalizes as well as the dense model. This is probably explain why it behaves similar to the dense model, but just running faster. Conclusions and future directions. In our early exploration of many sparsity patterns with complex training procedures, we found a simple pattern, butterfly plus low rank, consistently perform among the best. This motivates us to propose pixelated butterfly, which has fixed block sparsity pattern that align well with the modern hardware and was sufficient to yield workload training time speed up without sacrificing accuracy. Our model is the first step towards the goal of making sparse model train faster than dense and make them more accessible for the general machine learning community. And we're very excited about several future directions. First, we want to go beyond dense models. Many algorithms for exploiting model sparsity have long been used in scientific computing, for example, locality-sensitive hashing, butterfly factorization, and sparse models might unlock performance improvements in applications like PDE solving and MRI reconstruction. And the second one is the algorithm hardware co-design. Inspired by the remarkable success of model pruning for inference, it is possible that dynamic block sparse mask or butterfly could be made more efficient on the next generation of machine learning accelerators. And the last bit is the data sparsity. So in the near future, or maybe now, there will be a swing from the model-centric to data-centric machine learning, where the focus to study how data can shape what a model learns. So it is possible we can find structures in data and speed up training from a different angle. Thanks for coming to the talk, and I hope you enjoy it. Please contact us if you have any questions or are interested in those future directions. Yeah, I think that's the end of the talk.
Thank you so much, Beidi. I think we have a lot of questions on the YouTube chat. You don't have to worry about questions. I think we'll go through a bunch. And just a reminder to folks on YouTube, please, post your questions in the chat, and we'll try to get those to Beidi. Since there are a lot of questions, I'll actually start with a question from the audience. So I think Joey asked specifically about the butterfly factors. I think B1, B2, these matrices, and was wondering where these come from. I think they mentioned that they were on slide 10. Just to be clear, we can't see your slides anymore, but yeah, I think it would be nice if you could walk through again, the significance of the butterfly matrices and why people should care about those.
Yeah, so those are sparsity patterns, we have a nice diagram. We show the patterns, which is similar to like all this diagonal. This is actually very ancient algorithm. And it's from the, if you see the fast Fourier transform, it is like the same sparsity pattern. So we didn't create it, we adapt it. And what's new here, or not in this work, but earlier work in Kaleidoscope, is to make the fast Fourier transform like learnable. All these non-zero locations are no longer like fixed values. They can be learned. And that's why it resonates well with our new work, Pixelated Butterfly, because we basically can take the sparsity pattern and our weights are trainable.
And I just want to ask a quick, I guess, follow-up question, which I think also related to maybe a question in the audience. I guess like one thing that, I've noticed is sometimes when you like code up these like, sparse or low rank matrix vector multipliers or stuff in PyTorch, then what you find is that, unless you're like, say you take a order n square thing and make it order n, unless your matrices are particularly large,
right.
often, because it's not optimized for sparse or low rank operations, that you might end up actually being slower. And I know that can sometimes be the case for sparse, work in sparse matrices for deep learning. So I'm just curious what your take is on that. And if there's like, I think on the last slide you mentioned that there's maybe more to be done there, but just curious what your thoughts are there in terms of seeing actual, like sparse networks replace, non-sparse work.
Yeah. So for the sparsity, the biggest challenge is the supporting hardware. Because for example, like the GPU's V100 is like a block device. And if you have access to one of the entry in a matrix, you are supposed to retrieve like all the values in that block. It can be like a 16 by 16 or 32 by 32. So it's not efficient if you have arbitrary sparsity, because like in the end, you saw you were doing, theoretically, you're doing an ON computation. In the end, you're accessing the full matrix. So that's exactly why in Pixelated Butterfly, we have the first design is the block version. So we have to make it block sparse, which will take advantage of the block device like GPUs. Does that answer your question?
Yeah, I think that's a great answer. So it seems like there's a workaround for at least current hardware, but do you think that can be pushed a little bit more through?
So we actually have a detailed experiment or ablation study on if you vary in the block size of your hardware, you will have like better theoretical speed up, which means if you have a let's say GPU 2.0, which your block size is no longer 16 by 16, meaning that you access one value is you're not going to retrieve a 16 by 16 block memory access. You're retrieving like a 2 by 2 or like a 6 by 6. Then this is way more efficient for sparse training. So that's why we're super excited about the next generation of the accelerators.
Awesome. Thanks so much for the answer.
Hey, Beidi, I also saw a question from the audience that I thought was really interesting and actually something I was thinking about in the talk. So from the user Justice channel, they were wondering, is the 5.2x speed up, is this kind of a highly optimized value? Do you think there's still more room for improvement as kind of compute kernels improve? And I guess a more broader question, what do you think kind of is the high watermark for kind of speed ups or greater efficiency as you take this sparsity approach? Like if you project forward 5 to 10 years, what do you think is like, where do you think you'll be? What do you think the impacts of this line of research will have?
Yeah. So the theoretical speed up, we didn't compute it in this paper, but in my earlier exploration of the sparsity and the dynamic setting, which is particularly in Slide and Mongoose paper, theoretically 100 times speed up is possible.
Wow.
Yeah, but the problem is, like what I said, it's not compatible with the current hardware. And that's exactly why 2 years ago, or 3 years ago, I have to code everything from C++ for Slide just to get the speed up, like this kind of dynamic and random memory access, the kind of speed up for the dynamic sparsity. So that's why this Pixelated Butterfly is a big thing for me, because it's very simple method and several lines of code, and it just train faster. But definitely, we can see in the future, the sparse training will have a very high room to speed up more. Maybe not 100, but 10x and more should be there. And we're working on it.
That's really cool.
And I think it requires the effort both from the algorithm side and also the hardware side. And also the software side, like kernel.
Gotcha.
Yeah.
Yeah. I think this was related to another question I saw in the audience from Life in My Eyes. Can you change the structure of the butterfly matrix itself so that you can implement it on hardware? So this particular user mentioned a paper called it's spelled, I might be pronounced Iris, but it's spelled EYERISS. If you're familiar with that work, or have any thoughts on, changing the actual matrix itself to be more, hardware friendly.
So this one have like a short answer is yes. The long answer is if it's the original parameterization, which is the optimal one in theory, which Tree, our collaborator, has in his previous paper. I know he spent 6 months writing thousands of lines of CUDA code trying to optimize the original butterfly modification. And he still can't get it faster than like in the regime we're working on, or like the size of the matrix we're working on in this GPT or MLP-Mixer. It requires like really large matrix to see the benefits. But why the answer is yes is this will be our future work or the next work. We've currently working on a reparameterization of the butterfly matrix, which is exact and could be efficient on GPU. So maybe next time you will see this happening.
Well, really looking forward to seeing that.
So Beidi, when you talk about reparameterizing these matrices, are you talking about changing the structure of the butterfly matrix?
Yeah, you can. So remember, is like a divide and conquer. You can have log n factors, and the extreme case is the original dense matrix is one matrix, and the leaf one is log n matrix, but there is something in between. So it can be 2, 4, 8, and so on. And it is possible. So the idea is like it's possible to find somewhere which is still efficient on current hardware, but it's just losing something in theory, which won't affect the empirical performance.
I see. And this structure, would it be the same one reused across any different model you would want to learn? Or would it change depending on the model?
Because like the structure, the sparsity structure would be the same, but the numbers, the values in those non-zeros can be trained. So they will be different.
Got it. It's the same structure kind of for any model we want to use. So essentially we can fine tune a kernel to operate very quickly on this optimal structure, whatever one you end up finding in your next project. Yeah, very cool.
Hey, Beidi, one of the cool things that I noticed in one of your results slide was that I think on the like CFAR and ImageNet slide, I noticed that in some of the data sets, you actually got higher accuracy when you used sparse training, which is not something I would have kind of expected initially, kind of from first principles. Could you give us some intuition about kind of where you saw that lift coming from? Some idea about like kind of why that's happening? What are maybe some of the other hidden benefits of sparsity besides cheaper and faster execution and things like that?
Yeah, this is also one of our future direction, which is I believe in sparsity is not only to speed things up. It could possibly go beyond that and do things better. For example, like these structures can probably capture something related to FFT, which is like PDE solving, MRI images, reconstruction. But on the other side, even in our standard ML task, like language modeling or classification, it can serve as an inductive bias, right? So it could potentially go beyond what dense model can do. And in the end, people will say like you can have a fixed schema of the model and you do everything on data. I would say you can also have a fixed schema on model and just perform on the sparsity. You just vary the sparsity and you can get a better performance. And we do invest that a little bit. That shows up especially in images, like image classification, the accuracy improvement. We suspect because butterfly matrices is closely connected to the convolution, and which people know that CNN has very good inductive bias on images. And that's why I think, or we suspect, butterfly structures or butterfly sparsity can actually improve the performance of dense models or VIT and MLP-Mixer.
That's a really interesting perspective. Because the other interesting thing is you can also run it on these other tasks where you wouldn't necessarily think that that sparsity is, or that convolutions are kind of the right thing. Like you had those experiments about kind of these different text tasks and things like that. So it's just really fascinating that the same sparsity structure could, in one case give you a nice inductive bias similar to convolutions, and in another case do something where, something like transformers or, large language model structures are kind of more the norm.
Yeah. So it is a very nice inductive bias, we think, in general. We don't know how to prove that in images, but maybe in PDE and MRI, we'll able to show that soon.
So yeah, I'm maybe wanted to understand a little bit about, like I think you kind of looked at a lot of different applications. So you've talked through like text, images, and presumably you also run this on other data sets. It seems like you also run different tasks like classification versus generation problems. So I'm just curious, like, are there particular types of problems where this is more well suited? Like you said, like on image data, it seems like because you can interpret it as, coming from the FFT, and there's maybe some frequency space version that like you can view it in some frequency space doing something to the input or some like filtering kind of thing. So I'm just curious, are those kind of benefits similarly kind of interpreted in the language case where also like it's, you have data that's inherently discrete. So maybe it's doing something a little bit different. I'm just curious, how you think about that when you apply this sparsity pattern to different types of data.
Right. So surprisingly, in all the modality, it's just like doing really well. And we try to understand why that happens. And as you mentioned, we probably have a hypothesis for image data and for text, or maybe we should try the speech applications soon because FFT will, right? The FFT structure should do well there as well. And for the text, we currently don't have a very good explanation why it's connected to FFT. But since all the transformer models, efficient transformer models, for example, Big Bird, long former, and they have like this sparse plus low rank, but you can interpret it as global and local token mixing or connections. So we're suspecting that our, not particularly butterfly, but butterfly plus the low rank serve as kind of like mixing the token local and also global, and that kind of like capture enough information for the text data as well. So that's our hypothesis.
That's pretty interesting. And I'm curious, like just, following up on that, I guess, when you train, dense models, and then I wonder if you've tried to do something like pruning of like trained models into, let's say, a butterfly sparsity pattern, like taking a matrix and then trying to approximate it with a butterfly matrix or something like that for a trained model and seeing if that performance gap is small. Because I wonder if like the solutions that are found in the standard case when you just train dense models are very similar to the kind of solutions you find with the butterfly or pixelated butterfly case. Is that something that you might have seen?
Yeah, so we haven't done any experiments on the pixelated butterfly, but the good news is, for example, if you have a pre-trained model, let's say a GPT-2 or GPT-3, why you're curious about how we transfer that pre-trained model to a sparse model is you don't have to do this retraining again. And luckily, low rank structure, you can do low rank decomposition. And for butterfly matrices, you also have the butterfly factorization, which you can at least, I think the 3-way projection is not there yet, but at least the 2-way, you can, similar to like a 2 low rank matrices, you can decompose it into 2 butterfly matrices. So I think in this setting, we're able to distill or to project a pre-trained weights to a sparse model weights. I think that's doable. Yes.
That's actually pretty cool. Yeah. Thanks so much. Yeah, that sounds cool. Maybe somebody should do that for GPT-3 and see it and tell us.
Oh yeah. We're working on it.
I wanted to start, sourcing some of the questions from the actual class that we have. So one we have from one of our members in class. They were wondering if there were any like kind of anomalies or patterns that you noticed in Sparsity that led to higher increases in speed when applying Pixelated Butterfly. Like, are there any trends where Pixelated Butterfly gives you like more improvements in speed, or vice versa? Like, where are the situations where it might not work as well?
Yeah. So similar to all the other sparsities. So if your matrix is larger, you're going to have the actual speed up in time on GPU. You'll have like more savings or more benefits. So that's one. So for example, that transfer to the model size, like GPT-2 small will have like 768 by 3000 something. So for this matrix, it will probably have like a 2x speed up. But for the next one, which is like 1000 by 3000, then you're able to get a 2.5 times speed up. So the larger your model is, or the larger your matrix multiplier is, will have more benefits for Pixelated Butterfly.
Cool. So taking another question, you may be able to see this one in Zoom chat. So you concluded your talk by kind of mentioning some data-centric approaches. They're just wondering, could you, expand a bit more on what are kind of the opportunities you see in the space, how they might dovetail with your own research, et cetera?
Oh, yeah, sure. So I have been interested in how do you do data selection or data sampling while you train the model. For example, in my previous work, we can efficiently sample for each iteration. We can sample the important data to train on one iteration of SGD for linear regression. But I was always interested in the neural network model, which you don't have those theoretical properties or guarantees. So if you freeze one iteration, what would be the batch of data you want to train in that iteration? And that, I think, is depending on the structure of the data and maybe also the structure of the model as well. And that's like why I was interested in that in one of the future directions. So the ideal case is, there are two ideal cases. One is you can find a subset of the data sets, kind of like a core set, that you only need to train on those sets to get the same accuracy. That's more efficient. The second one is, even you can't do that for each of the iteration of the model, or like given the model weights, what would be the optimal batch of the samples you want to train on that iteration and to converge faster. And that's another way to improve the training efficiency. So yeah.
Yeah, that's really cool. It reminds me of a talk that we had last quarter from Baharan Suleiman. Yeah, really, really great stuff. I mean, she was also a postdoc at Stanford back in the day. So maybe it's just, postdocs at Stanford come up with great ideas.
Thank you.
I was going to also grab one more question that I think we missed in the YouTube chat, which was, I think Justice Channel asked if you could contrast your work, and I feel free to say no if you haven't seen this particular work, but the work is called Dense for the Price of Sparse, I think, out of Oxford last year. So I think they were just curious if you could contrast what you've talked through.
I heard about this paper, but I haven't read it.
That's
so yeah,
totally fine. Yeah, there are too many papers on archives, so
But I think I heard about this paper. Yeah.
Okay. Well, maybe
Yeah, I'll take a read offline.
Yeah, just a channel. You can
feel free
email.
to draw me an email. Yeah. And I will take a read. And if you have any questions or any comments you want me to make, we can communicate offline.
Awesome. Yeah, that sounds great. And I think another person, Nikhil, had a question about code and also, how do they run Pixelated Butterfly and stuff? So you have code out, and is that something that they can use?
Oh yeah. So I think in the paper we have the link, and in the slide, if you can go back to the live stream, the last slide had the link to the code and the paper. And if you can't find it, just drop me an email, and yeah, I will send it to you.
Awesome. So I think we're coming close to the end of this. So I want to ask you a couple maybe questions that are more future looking. In particular, I'm pretty curious about what you're excited about next. I know you had that last slide where you said some of the directions that you would be excited to work on. So what are some of the things that you think either we probably have folks in the audience who work on Sparsity themselves, or people who are curious about this, what can they do in their research, or if they're working at companies, in machine learning teams and stuff, to actually start to use some of this in their own work, and where are you excited about other people pushing on this? So
so those three directions are not only for the follow-up of the paper, but also for my own research interest. So I will probably give more details for each of them. So the first one is like going beyond dense models. We have already had several discussions in the previous 20 minutes on sparsity can be a better inductive bias. beyond efficiency, right? So that's very exciting. And how can we use that inductive bias? I think it's not only for the machine learning applications. It could be like the scientific computing that I'm very interested in, and also like for the medical image domain. So for all the randomized algorithms, or like all this randomized lineage algebra I've been used, they have been heavily studied in those domains. So I'm pretty confident we'll find something interesting in this direction, sparsity for scientific computing or medical imaging. So the second one is more about further speed up. And that's a great question from Dan, like, how do I view the future of sparsity? I think it has a bright future. There have been great researchers and also startups working on different architecture design of the chips. And sometimes like I just feel that if I only work on the algorithm itself, I'm always bounded by the hardware limitation. So that's why like this Pixelated Butterfly, that's the first step towards you have to consider or take the hardware constraint into consideration. And then on the other side, or going further, why don't we design things together? And also not only the hardware, I mentioned like the software is also very important. For example, like the compiler. And also for those specialized kernels. So for example, if you, even the hardware can support something, and in algorithm level, you also have some speed up. But if you don't have a support support software, you cannot realize the speed up. So I would view this as like algorithm, software, and hardware co-design. So I think that's like a future way to go for sparsity being more efficient. The last one for the data sparsity, yes, I think there are a lot of questions that we don't understand in the data. And currently, we just realize it's hard to further optimize the model. And that's why there's a swing back to data-centric machine learning, and Karan, you're expert on that.
Thanks for the plug there.
And people find like data augmentation or just using more data can also improve the performance, or by a lot, than just optimizing the model architecture, right? But I don't think that's like well understand for now. So I think for this part, it needs more understanding before you propose anything new. And especially for neural network, there are a lot of things we don't understand yet. So if adding the data as the factor is more complicated, and yeah, maybe more data is necessary, maybe not. And maybe the important data is necessary. So that's like how I see this line for going forward.
Awesome. That was a great answer. I think that was, I know you're also on the job market. So, good luck with that. And hopefully there are a few folks watching who, I was very impressed by this talk, but I hope, there are folks watching who are excited about your work. And I think it's like really interesting future direction. So hopefully more folks get into sparsity too through this talk.
Yeah, as being like, being on the job market, I think it's like excellent opportunity that you can like zoom out a little bit from the research or like the real technical problems you have been doing every day, and think about what would be the future like, and what directions you're interested in, how you want to make the impact, which is actually very, very interesting. And I enjoy it.
Yeah.
And you get to chance to talk to a lot of people.
Yeah, one of the things I was thinking about through this talk is it seems like sparsity is kind of, really fundamental to like how like to intelligence and like how people's brain works. Like you hear this stat a lot that, oh, we only use like 10% of the brain or something. And seeing all your work, it's like, oh, maybe we should only be using 10% of the neural network as well. So I think, it's a really exciting direction, really, fundamental question and line of research that you're looking at here.
Yeah, for the sparsity, it's definitely related to the neuroscience part, and people all like brain efficiency, right? So you have to think about so many things, and you don't consume too much power or CO2. So hopefully we can realize that someday. It's hard, but it's possible.
Awesome. Yeah, I was gonna say like the 2%. I'm not sure if that's a myth or not actually. And I remember there was a joke about how Einstein used like maybe a couple of percent extra, which I always found very funny. Like we're like maybe use 3% instead of 2.
Well, if you watch that movie Lucy, you should know that if a human uses 100% of their brain, they become like a god. So I think maybe the way forward is train neural networks with sparsity, then go back to dense, and then we can do anything.
Yeah, I haven't seen Lucy, but
I think Beidi used at least 50% of her brain to come up with Pixelated Butterfly.
Me 50%, and then Tree 50%. We have 100%.
That's the secret. That's how you run a lab.
Oh, yeah. Collaborations.
Right, awesome. I think we're pretty much at time, so this seems like a great time to close. Yeah, thanks so much for everybody in the audience on YouTube who tuned in. And since we're back again, we're going to be running the seminar series over the course of this quarter, which is winter quarter at Stanford. So we'll be back every week again, in case you missed us. And as always, subscribe to the channel and join our mailing list if you want to, see what talks are coming up. We don't spam. We only send up to a mail a week, so it's pretty nice, no ads. And I think next week, Dan, who do we have next week?
Next week we've got Deepak Narayanan. I think I said that right. He was a postdoc at Stanford. Now he's up at MSR.
I like how you were prepared because I always forget to check.
You can train me too. I'm just like a machine learning model.
Did he train the Megatron?
Yes. Yeah. That was Deepak.
And he was a PhD student, not a postdoc.
Ah, yes. Well, I promoted him in my mind.
All right. See you, everyone. Bye.
Bye, everyone.
Bye.